Now it's a true pleasure now to announce the final section of the symposium, the final 3 talks, and a real finishing up on a very high note, a real high caliber of speakers in this last session that are covering particularly global change modeling for biodiversity. And first we'll start out with Rob Guralnick, who is a leader in biodiversity informatics as well as biodiversity change analysis. He's also co-instigator of the Map of Life project that I talked about yesterday. And he'll be talking about the new vast machine, challenges and solutions to documenting global biodiversity and its change.
Thank you, Walter. And my honest appreciation and thanks to the Yale Institute of Biospheric Studies for extending the invitation to come here and have a chance to interact with some amazing folks doing remarkable research working in the policy domain. What I want to do today is talk about some challenges, it's in the talk title here, of documenting global biodiversity and its change and looking for solutions. And in some ways, this talk nicely dovetails and reinforces a lot of the core messages that you've heard throughout the last few hours and over the last couple of days. But unlike those other talks, I focus more on this talk from the perspective of someone working in the emerging area of biodiversity informatics. And really what I hope that I can convince you is that the integration of informatics approaches and working in a big data kind of framework really does bridge nicely with global change biology and moves us into the arena of bringing information and computer sciences to bear on the key challenges that we face in the arena that we're working in. And so you might wonder about this provocative first couple words on the slide here, this new vast machine. And I refer to the new vast machine as a riff on a book title called A Vast Machine that details how climatologists have effectively built this machinery to approach global scale monitoring and ultimately forecasting. And so Paul Edwards, who's the author of A Vast Machine, makes a set of excellent points about distinguishing what he refers to as making global data from making data global. And so I want to just give you a quote that kind of covers his view on making global data and making data global. So making global data, and this is a quote from the book, is collecting planetary data in standard forms through interconnected networks to build data images of global weather and general circulation. He contrasts this to making data global, which is loud, and I'm getting a finger. And his quote here is that making data global is about building complete, coherent, and consistent global data sets from incomplete, inconsistent, and heterogeneous data sources. And what I really want to come to here is this transition point from work in aggregating and pulling together data and information and knowledge, and then integrating it and creating these final products that get us to this idea of making data global. And an essential point I think that I want to bring home again, and it's been mentioned so many times during the course of the last couple of days, is the idea of not just monitoring and tracking from the recent past to the present or going forward in time and watching the world change. It really is coming back to this key idea of forecasting, of being able to forecast the velocities of change, whether it's in climatology or whether it's in biodiversity sciences. So this requires us, and if we think about the challenge of making global data, the challenge of making global data is big compilation. It's big data challenges, and it's ridiculously and remarkably heterogeneous. So we have all these questions we want to know about life on the planet and what's happening to it. We need to know what data sources to pull and where those data sources are and how to compile more of those. But we really have, in relation to biodiversity, these key challenges of looking at the genetic and species and ecosystem level diversity. We need to pull those resources into one spot. So we have this image here where you can think about the molecular side, where we have molecular data, genes and genomes coming in. We have our species knowledge that comes from the legacy literature and describes our 300-year cataloging and compilation of knowledge about where species are found and what's out there. And then the ecological frame, the abiotic and biotic context that pulls this all together and puts us right in the middle spot of what we're trying to do in the big compilation, the big data challenges that we face. And of course, we have seen many examples, and I've already effectively covered this in multiple different ways, but just to remind you just once more, that it absolutely matters. We know that our systems are effectively reaching a level of crisis. We'll look at some measures of population indices that start off in 1970 and run to 2000. And forward, we can see that there are rapid declines in many of our systems, and freshwater systems in particular, but certainly impacts in terrestrial and marine arenas. And the Earth's biocapacity, its carrying capacity, has been effectively, at this point, exceeded by our needs that we have as a species for food and fuel and fiber and feed. And that means that we're now at a point where we're not able to replenish our resources. We're using up more than we're gaining back over time. And that leads to John Hoekstra's remarkable talk and points about resource scarcity being a big driver of our future as we have an increasing population with increasing needs for food and fuel and fiber and feed. And of course, during crisis events, for example, a Gulf Coast oil spill, we want to be able to predict how biodiversity and industries like seafood industries will be impacted. Without the resources available to compile that knowledge and be able to act on it quickly, we're going to be at a point where we don't know the outcomes not only of constant and accelerating changes, but also during these crisis events where we have major changes happening to the environment and that are unexpected. So the challenge, I mentioned challenges and solutions. I want to cover some key challenges that span a relatively wide range of where we are in the biodiversity arena that brings us out of just simply thinking about species distribution data, but also a lot of other key impediments. There's the Darwinian Shortfall, which is well documented in the literature. We don't know, we've documented somewhere between 1 to 10% probably of the known species on the planet. So 90% of our diversity is still unknown, is out there for discovery. And we have an antiquated and laborious practice of documenting that diversity. Walter's really nicely talked about the Darwinian Shortfall, that slide that shows the knowledge gap between our remote sensing data and data coming from species distributions is really clear. And so that's a major shortfall we need to cover. I made up my own one shortfall that hasn't quite been described yet. I'm calling it the Darwinian Shortfall. There's no framework for assembly and integration of our phylogenetic knowledge. There's a new project called Open Tree of Life that will get us further downstream to building a global and comprehensive tree or forest of trees. But right now that framework is missing. And this is one that comes from Holger Kraft. It's called the Humboldtian Shortfall. And it really is that we lack a comprehensive set of trait databases. Those are beginning to be assembled and put together, but a lot of times we're lacking a consistent metrology and set of standards for making sense of the large-scale trait data sources. And on the positive side and on the negative side both, we are opening up our pipelines wider and wider to pull in data to help to deal with these impediments. But at the same time, we have what's called the big data challenge, which simply means that as these pipelines continue to widen and widen, at rates that are increasing by the day and by the year. If you think about sequencing, for example, in particular, where the rate of sequencing is and the cost of sequencing is going down by orders of magnitude each year, well above Moore's law's threshold. We have this deluge of data coming towards us, and we don't always have the techniques and the processing power to turn those data into knowledge. So what are some of the solutions to these impediments? Well, one argument I'm going to make as someone who's really bridged into information science and tries to find a balance point between global change biology and information science is that we need to have repositories that can store this information for the long term. And these data for the long term, and to be able to describe them well enough so they're very, very usable and linkable. And so some of the key repositories that we have and we're developing when it comes to taxon concepts, names, and the meaning of names, we have things like Catalog of Life, Worms, and IDIS, and EOL, and GNA, Global Names Architecture. EOL has name services, and there's the GBIF Name Usage Bank. On the geography side, the big one is Map of Life. Map of Life right here is really one that assembles knowledge from a bunch of different sources and pulls it all together. It's really a key place where we're going to be building our spatial biodiversity knowledge. I'm going to come to Map of Life in a little bit and touch on that in ways that Walter didn't get a chance to cover entirely during his presentation. With genes and genomes, we have things like GenBank and TreeBase. We have a new Open Tree of Life project. We have the Barcode of Life database and TreeBase. These are all ways to compile knowledge about phylogenies and hopefully have that be part of the mix in biodiversity. And with phenotypes and traits, we're building those databases now, whether it's MorphBank or this traits database, or ways to describe the phenotypes more effectively using new approaches and ontological approaches like Phenoscape. And these are all built around a key concept that Paul Edwards in The Vast Machine talks about at length: standards. Boring stuff, the glue or the infrastructure, the plumbing that holds this all together, is having a way to have interoperable, discoverable data that you can find that is represented in ways that we understand how to do that discovery effectively. And so standards reduce data friction. They allow data to come together in ways that build data that is global. And so the natural history community in particular has developed one standard that's touched on it briefly called Darwin Core, kind of an evocative image of the idea of a Darwin Core here in this painting. And Darwin Core is a standard that currently pulls together 500 million species occurrence records in a common format and allows them to be used in aggregators like Map of Life. And there's also, importantly, a standard publishing format for Darwin Core records called the Darwin Core Archive that is really useful if you're trying to aggregate records and pull them from this ground-up perspective, this bottom-up perspective of making global data, where you really want to pull those heterogeneous data sources together and put them someplace where they can begin to be used before we make data global. And so one example of this is VertNet. I just want to cover this briefly because it shows you what's happened in just a very short period of time, in 10 years. In 1999, when the first networks came online for serving vertebrate biodiversity records, this was called MANIS, the Mammal Networked Information System. There were about 6 institutions at a cost of about $14,000 a year, providing about 1 million records. By 2010, the number of vertebrate biodiversity records that were being served over networks was at 171 institutions serving about 80 million records, with 52 institutions on a waiting list wanting to become part of these networks, but not having, we didn't have the resources or the person power to basically pull those institutions onto the network at a spiraling cost of about $200,000 a year just to upkeep the networks. So VertNet, which is a project that compiles all of these different networks, whether it's mammals or birds for ORNIS or herps for HerpNet or fish for FishNet, is scaling down the costs and increasing the scalability. So it's cheaper to sustain and scales infinitely in terms of being able to support the growing amount of data coming into these networks. And so by 2013, we'll have 223 institutions providing about 100 million records at a cost of about $12,000 per year, which is a remarkable decrease because we are using an infrastructure that is cheap and it works really well and is super scalable. The idea being that we have these Darwin Core archived data files that come from providers that are in Darwin Core format. They're harvested and created and put into a single large CSV file. These are processed in a MapReduce framework, which is a big data framework for elastic computing, allows us to index these really quickly and really effectively, really cheaply, output these into PostgreSQL databases that have mapping applications built on top of them, and they can be immediately accessible via the cloud. And so this big data framework for taking a lot of data, we're talking about hundreds of millions of records and making it available really effectively, quickly, and cheaply, is a big task that we face in moving forward in that goal of making global data. And of course, we want to find out the fitness for use and want to know the quality of these data. Data quality is so essential and often neglected, but the key thing is that across this large network of data coming online in terms of integrating, aggregating, and making interoperable data out there that's usable, we have a lot of errors in these data. We can see that about 4% of GBIF records contain at least one type of a number of very, very easy errors to find. They're really, really simple ones that you can just immediately check at the records and say, there's got to be a problem. And there are more subtle errors in these record sets as well that need to be flagged and checked. And many people have talked about the importance of flagging and checking these errors. But out of those 4% of the records that have like obvious, like, oh my gosh, these are clearly wrong, about 54% of those have one kind of problem. The coordinates, the lat-long coordinates fall outside the country, specified country that is listed on the record. And you can see that there are a whole cascading set of very, very simple errors. Like 33% of those errors are basically no data being recorded at 0, 0 locations. So if you plot GBIF data on a map, you get a ton of records at 0 degrees latitude, 0 degrees longitude, because they're recorded as 0, 0s instead of no data. And there's a whole set of other errors. 8.1% are just transpositions. I mean, very easy things to fix that will help make those data more usable down the road. And then all those data sources that are now being linked up. And so we have projects like EOL serving as core aggregators, taking in data from GBIF and from NCBI or from all these other sources that really allow the data to propagate out from their silos, from their individual databases into this broader world of linked data where everything links up and is effectively brought together into a single context. But one thing you'll note is although there's obviously remarkable progress in building out these networks of networks and interlinking these data sources, and there's a growing constellation of biodiversity data and knowledge, there are a number of database projects out here that are just not linked up. And those are effectively at risk for not being sustained very well into the future. And it's a lot of resources and allocation spent on building databases that never last more than a few years. And so we'd love to see those resources brought into this network. And it's one reason why Map of Life can be very powerful, I think, is that it serves as a way of bringing in some of these databases and resources that are kind of out there in no man's land. So how do we link all these data together? Believe it or not, I have a Facebook friend. I know that sounds remarkable. This is a fellow that I work with on linked data projects called John Deck. And if you think about the fact that you make friends on Facebook and you click a link and you say, this person's going to be my friend, you can imagine the fact that you can draw graphs out that show you friends and your list of friends out here, whether it's Tim White up over here or anyone else. And if you look at how Facebook operates, they basically have a model, an ontology based on what's called a friend of a friend approach, where you can kind of do 6 degrees of separation. You can follow friends all the way down a chain and track those relationships. You can filter them based on marriage status or on gender statuses or on number of interconnections. The reason I bring this up is because you can take the same approach to tracking data in a web context by really thinking about that model of tracking relationships over a set of friends, but you can think about tracking relationships over a set of digital objects that spool off from collecting events. So if you go out and you collect and you have specimens that you bring back in and you photograph them and you have metadata records regarding where those were found and when they were found, and you look at the genomes or gene sequences from these things, it's going to all be put into a tracking system where you can begin to link those up and then filter on characteristics that you want, whether it's filtering by specimens or tissues or images or sequences, or whether it's filtering by taxonomy and getting the records that you want that are linked up in this vast linked up web of data objects that are out there. That's how we're going to do science in the future. It's how we're doing it now. Everything we do is effectively brought into a digital frame. So linking those resources up is really, really essential. So linking, standardizing, improving, and integrating data transitions us from this first part of the talk, which is simply about the idea of making global data, kind of aggregating up from the bottom, pulling it all together and looking at how we can begin to operate on that and analyze it, to making data global, to really doing something with those data, to integrate it and to make knowledge. What I argue is that we've been very close to this workshop symposium. This whole symposium, we've kind of come back to this core idea that somehow there's a virtuous cycle where we're going to create new kinds of knowledge by basically having initial kinds of questions. Can we better document the distribution of organisms on the planet? We're going to have a set of repositories that are going to be growing and growing as we digitize and create standardized raw views or of these from these digitization efforts. We're going to have tools and application services and analytical methods, these growing toolboxes that link up these repositories and tools. And these will start to create a cycle where we can link those all together in this large world of data and basically go from having these initial research questions to new kinds of research questions that integrate new knowledge products. And that kind of creates what I would call a virtuous informatics cycle. You can loop through the cycle, you can create knowledge more quickly, answer questions more effectively. That's really important for what Map of Life and other projects and other work we've heard about is that we're increasing the scale of data. We want to be able to turn it into knowledge more effectively for decision making, for policy, for better science. And this is the kind of loop we're going to have to run in the future. If we have to be in the position of doing this. That's the way that science is already working in the 21st century. It really is making not only integrated data global, but making integrated knowledge global in the sense that we have data repositories here that then feed in and create new knowledge that gets stored along with that original data, and data the models iterate through that cycle. So I wanted to just briefly come back to Map of Life. Walter brilliantly touched on much of what makes Map of Life work and how it works. I'm just going to cover some of the parts and pieces that he didn't get a chance to cover in full detail. It's clearly a collaboratively developed project and community and a framework and platform for integrating biogeographic knowledge. And it's a means to also generate and store much finer modeled outputs. But also, I want to come back to a key thing. Map of Life is really about people. It's about working collaboratively and collectively in a curatorial context. As a curator, I find this really powerful. It's a workbench for users to perform individual model integration, as well as a mechanism to contribute their own knowledge and make maps better. And importantly, it's a tool for discovery of biodiversity patterns. And we want to talk more about that, I think, down the road about how Map of Life is creating knowledge products that are beyond just simply the distribution products, but look at things like species richness and patterns of turnover over space and time. Map of Life is really about data. I don't know if you had a chance to see this on Map of Life when you were exploring it on your own. Hopefully you've all had a chance to do that. This is our data dashboard, and what it shows you is that we have about 40 data sets right now. We're growing this extensively, pulling in data. Cody's in the audience, and not as we speak, but pretty much we're growing the number of data sets we're ingesting. We currently have about 90,000 species in Map of Life, and we have about 150 million data records. And really importantly, we are really clear about providing attribution and citation back to the original providers. The original providers have to be told that they can immediately see that their data is on Map of Life, and they have to be able to get reports and knowledge generated from Map of Life about how their data are being used. It's going to be critical for us to make the case that you get value, and you're going to get continued value for making data available in this kind of way. Map of Life is about models. I already covered this. I'm just going to go right on and just say that you saw the great ways that we can begin to think about modeling all these different data sources and deal with the heterogeneity. And most importantly, Map of Life really is about people. You've seen this slide before, but I want to just remind it again, we've got people working up here on producing data, bringing it into Map of Life, really working to help people do that is a big part of what Map of Life is all about, and to gain credit for that. It brings that into a repository, a knowledge repository where you can do things like overlay data, do first level integrations, create model products, whether it's binary threshold maps showing distributions, or whether we're looking at probabilistic assessments per pixel over a range of a taxon, and importantly, model uncertainty, so we know that we can report what we don't know. And also, I just want to point out again the importance of having workbenches where users can interact with these data and other kinds of ancillary information to basically create their own models and do their own map alterations. And very, very importantly, at the back end, we have all these different use cases for people who want to come in and use these data, whether it's a mobile user generating a localized species list while they're going to a national park, whether it's a naturalist who wants habitat preference data for a taxon, or localized habitat maps, whether it's a land manager or scientist. These are all fed to these consumers down over here. And then, of course, we want to make those data available to other knowledge generators like Encyclopedia of Life, who can access these data and provide them back out to their users, integrate those into the broader realm of data resources out there. It integrates really brilliantly and beautifully with citizen science. And one thing that I made this slide a few days ago, but Zooniverse came up in conversations this morning among some of the participants. And what I want to really drive home here is that when it comes to citizen science and integrating citizen science into Map of Life, we're talking about basically people doing classification tasks, like checking data, making sure that the data are correct. When we do this, the key thing that has been shown by Zooniverse is really simple. If you want people to come and do tasks and crowdsource tasks, the way to make that work is to tell a compelling scientific story. I can think of no story more scientifically compelling about our planet than our impact and how people can be involved in helping to tell that story. By doing so, educate the, people who otherwise not have a chance to do it about the importance of the mission of really working to understand how our planet's being impacted by our actions. And then also providing incentives and even digital rewards, badges. It sounds really, really silly to us, but it's been shown again and again in the education literature that making reward systems, even digital objects, they don't have to be physical rewards. They still seem to affect the same part of your brain that likes getting rewards. So this is how people play those silly games on Facebook. But we think that not silly at all is providing people rewards for basically involving themselves in the process of doing science. Whether it's someone who does a lot of activity across the globe on Map of Life and gets a Globetrotter badge, or works particularly in birds and gets a flock spotting badge. Those are ways that we're going to be able to incentivize and provide reward systems that will get people to be participatory in working on these kinds of projects. So what I want to do, and I'm almost closing in on what I wanted to talk about here. I'm just going to go for a couple more minutes. I wanted to tell you one thing. Walter really correctly said something yesterday that a lot of our challenges are sociological, not technological. However, if you go to mappinglife.org and you were to wait 10 minutes for a result to come back from our application, or any application, you would be frustrated and leave. You would not want to spend your time waiting for results to come back. So there is a technological imperative to basically make the application work quickly. And I want to tell you a little bit about how we've done that from an informatics perspective. Map of Life has a front end that we leverage using Google App Engine for indexing a whole list of our taxa. When you search on that list, you get a result relatively quickly from that indexed list. It goes out to a backend that includes a Postgres database and a mapping stack that is really quick at returning those results as tiles to your browser. And effectively, that is in a short summary how it works, and a little bit of a more exploded or expanded view of how this works. You have these checklist and range and ecoregion data sets and points coming in to the staging area. The points come through GBIF and then get pulled in. These get put into a production site that allows access via an API. There's actually a catching system that has allows us to globally pull. It allows different areas in the world to be able to access that catch really quickly and effectively. That then connects back out to this API for access from other resources or to a browser and that index so that people can access the product. It's a very simple architecture, but it actually brings us into the frame of doing big data and being able to support a lot of very, very, very quick returns of results to your browser. So I want to end here by actually just coming back to where we started this session. Walter mentioned we're talking about how to better document and forecast change. Well, I want to talk briefly about a project that I've been involved in, and actually Walter Yatz and Brian McGill are also involved in, that Walter touched on very briefly, that ties very, very closely to Map of Life. It really comes down to how we're going to be able to do that forecasting process. So we talked at the beginning of this talk about the idea of a new vast machine. And what I want to comment at the end here is how we're going to begin to come to the point of forecasting. The big thing I want to say is that we've got tons of challenges here. It's not an easy area to be working in, but one simple way to kind of conceptualize what we can do as a starting point is we can ask ourselves, what is the general trends that we're seeing from the recent past to the present? Do that calibration, track those trends over, say, a 40-year time frame, and then see if we can begin to use that kind of calibration to allow us to track changes into the future. So the idea behind that is to actually do something really quite difficult at the start, which is to create a set of environmental data layers that range over a 40-year time frame that reflect daily or monthly climatologies over 40 years. So we're creating for the globe at 1 kilometer scale resolution a set of layers that reflect our knowledge about climate over the last 40 years and also land cover. we want to do something that I think is really simple, but actually a bit profound, and because in the niche modeling literature it hasn't been done a whole lot, is to associate the date of collection and the location of collection to that point in that stack of layers. So you have a stack of layers, and you say, well, when was this collected? What were the conditions, literally, in that stack of layers and that date? Pull that layer out, annotate that record with the conditions of the time of that collection. A really simple process, but one that allows us to begin to look at trends, right? So if you have that date for a point, and you have 1,000 points for a species, and you have 1,000 species, you can begin to link all those up and look at temporal trends. And then one simple way to look at these patterns and start making sense of them is to basically model niches and distributions over 2 different time periods, say from the 1970s through 90s and then 1990s through the teens. And then you could also do this kind of look at changes in environment and focal species occurrences in reserves. So what's the velocity of change in climate in a reserve area? What is the velocity of change biodiversity for species in a reserve over that time period? One of the important things about this approach is that when you're talking about this change assessment method, we're talking about doing this over thousands of species, not 1 or 5 or 10 or 100, but literally where the data allows us, where we have enough records over those 2 time periods to begin to look at these patterns of change, where we have well-documented species, but also running those as new data comes in. We expect the world to increase in terms of data making global data, and so we can more effectively go from making global data to making data global by working on this method as it comes available. So in a nutshell, and quickly, and I'm almost done, we have our period 1 time from here with our layers over those 20 years for topography and land cover and precipitation temperature. We have period 2 over here over the 1990s through the teens. And we take observed occurrence data over in that 20-year bin for a particular taxon, and we're able to use that to do some modeling, niche modeling approaches. There's many different ways to slice the pie on doing the niche modeling, but we'll create a niche assessment for that period 1 and for period 2. We can look at the delta. We can look at the species niche shift. We can do the same for range by looking at the observed occurrence data for those 2 time frames. And from that, we can begin to ask simple questions about, for a taxon, do we have a situation where we're seeing changes in distribution, but no change in niche, which we might think about as something akin to climate tracking, or conversely, we might see a situation where we see a change in the niche, but not in the distribution of the taxon over those 2 time periods. Or we might see a mix of patterns. And over thousands of species, we can begin to look at traits and other characteristics of those species to find out if there are some explanatory variables that allow us to look at what we're seeing in terms of these different patterns. And so in summary, I guess I'd say that map of life is not simply a static way of viewing the world. It's also one that involves looking at change and change analyses, whether it's range persistence or loss or gain, and uncertainties about that. And in a way, that brings us to the place where we started, which is that the pieces are in place for a new vast machine. I think can completely transform how we monitor the planet's pulse. With that, thank you.
Thanks a lot, Rob. We have time for 1 or 2 questions. But, Derek, feel free to read.
Catherine, please.
It's a naive question, but I remember in the beginning when people were talking about databases and all this stuff, that they were really distributed and that they went to, the idea was a bit of a collection with whatever museum, had the data, so if the curator made a change in the late morning, then that was available for everybody. Really big thing. And I'm just wondering, this one's much more complex and bigger. Are we maintaining that true database nature, or is it somehow being redefined?
It's becoming a hybrid. And that's a great question. The initial systems were distributed for 2 reasons. One is that the museum community wanted to have a level of control over the original data, which is absolutely and 100% reasonable. But over time, as these resources have proven their value, so one of the key stats I love repeating is that we're seeing about 3 million hits a week, data requests a week for VertNet data. So these are really highly used resources. As they've grown, the system has become very cumbersome in the sense that every single one of those distributed databases had to be up and running for you to get the consistent result returns from a database query. So if you went in one day and searched, and you came in another day and searched, you find different results depending on who's up or who's down. So what we've done is we've created a system where there are still live connections between those databases, but there is a data store, a cache of data, so that if one provider is down, you can access that local data instead as an indexed copy of what was online from that provider. And that provides a level of sanity in this kind of growing, proliferating world of like thousands of databases being connected into the system. It also allows us to do things like actually report back statistics more effectively to the providers.